Slip yourself behind the controls of this metal beast. Feel the crushing weight, 45 tons grinding forward through narrow metal treads. Your fingers work the controls, moving them slowly, as if pushing through thick honey on a frozen winter day. Behind you sits the engine, temperamental and angry. It roars without warning, an unpredictable machine that could simply quit without reason. Welcome to the Panther. This was Germany's supposed masterpiece, their tank of tanks. Yet this remarkable machine spent more time broken down than fighting, more hours in repair shops than rolling across battlefields. What would happen when American tankers got their hands on these captured German machines would demolish everything they thought they knew about tank combat. It would force a complete rethinking of one of history's greatest engineering puzzles. The winter of 1944, snow blankets the Ardennes forest. American tank crews huddle inside their Shermans, watching. Through the mist, German armor appears. Panthers, sleek, deadly, cutting through the white landscape like predators. 45 tons of sloped steel, a gun that fires shells at tremendous speed, 75mm rounds designed to punch through anything. Every American tanker had heard the talk at base camps, around fires, in quiet moments. One Panther could handle 5 Shermans. Easily. That was the rumor. The numbers were there to back it up. Germany's Panther featured frontal armor angled at 55 degrees, 80mm thick, which gave protection equal to 139mm of straight plating. The turret added 100mm of steel. The main gun could pierce a Sherman's side armor from over 2,000 meters away. American soldiers had a dark joke about their tanks. They called them Ronsons, named after a cigarette brand. Because Ronsons, they said grimly, light every time. The crews climbing into those 33-ton Shermans that frozen December morning understood what the numbers meant. They understood the Panther outmatched them completely. Its armor shrugged off American 75mm shells firing from the front. In a long-range duel, they stood no chance. The Germans knew it too. Their commanding officers had hammered it into their heads. Your Panther is unstoppable. American tanks are toys, nothing compared to German engineering. Propaganda films showed Panthers crushing Shermans with casual ease, German steel proving its dominance over American mass-produced weakness. The Panther had emerged from a specific need. German commanders wanted something to counter the Soviet T-34 tank. When German forces encountered the T-34 during their invasion of the Soviet Union in 1941, particularly at the Battle of Metsensk in October of that year, they were shocked. German high command moved quickly. They assembled a special investigation team focused entirely on armor design. In November 1941, the Panther Commission formed. A design submitted by Mann was chosen in May 1942. The first Panther rolled off the assembly line in prototype form by September 1942. Full production started in January 1943. On paper, everything looked perfect. The ultimate medium tank, surpassing competitors in nearly every technical category. The German machine seemed flawless. Yet as American forces pushed into German territory, something unexpected began happening. Tank recovery crews started encountering Panthers abandoned on roadsides, not destroyed by enemy fire, not crippled by mines, simply left behind by crews who had walked away. Engines cold, diesel still sloshing in fuel tanks, transmissions frozen, drive systems shattered beyond quick repair. Some captured Panthers did see action. The British assigned one to a unit and gave it the name Kudu. It saw fighting at Geister Castle in late 1944 and during Operation Blackcock in January 1945. Canadian soldiers captured an intact Panther in Italy in October 1944. They called it the Deserter. They used it in several attacks before sending it to be studied by experts. Polish resistance fighters grabbed 2 Panthers during the Warsaw Uprising in August 1944. These machines destroyed German gun positions and helped liberate prisoners from the Jenisovka concentration camp, freeing 348 people. Within days, though, both Panthers couldn't move. No fuel. Batteries dead. The soldiers set them on fire to prevent Germans recapturing them. The story repeated itself constantly. Captured Panthers could fight effectively for short bursts. Then mechanical failure stopped them cold. After the war, the British decided to test this claim. They built 9 Panthers using German parts and German technicians who had surrendered. In 1947, they tried standard military trials. The Panthers kept breaking. Tests couldn't be completed. Machines simply failed. The British assessment was blunt. Very little useful information could be obtained because of the Panther's fundamental mechanical unreliability. The French military conducted the most thorough evaluation. They used captured Panthers in actual operations from 1946 to 1950. Their 1947 technical report, titled Le Panther, stated the problem directly. The greatest weakness of the Panther is its final drive, which has a fundamentally flawed design and an average service life of only 150 kilometers. Let that sink in. 150 kilometers, that's roughly 100 miles. Before the final drive, the mechanism transferring power from the engine to the tracks required complete replacement. German wartime documents proved this devastating failure rate existed. General Guderian himself wrote in June 1944 that the Panther's motor could run between 1,400 to 1,500 kilometers, but the final drive failed much faster. He wrote that solving the final drive catastrophe was urgent. An Eastern Front report from March through April 1944 documented reality on the ground. In just 1 month, 30 Panthers required 13 final drive replacements. By January 1945, a Panzer Commission report listed 370 defective final drives removed from Panthers needing replacement. When examining Panthers abandoned in Normandy, roughly half showed final drive failure as the main mechanical problem. The reason was understood perfectly by German engineers. Mann's original design called for a planetary gearing system, but German factories faced shortages in machinery needed to cut gears precisely, so they switched to double spur gears instead. This system created higher internal stresses and more destructive impact forces inside the drive. Here was the killer. The drive system had been engineered for a lighter tank, meant to weigh 30 to 35 tons, but Hitler personally demanded more armor and a bigger gun during development. The finished Panther weighed 45 tons. The final drive housings, built for the lighter vehicle, couldn't handle this extra weight. When the tank moved, the housings flexed. Gears inside ground together, destroying themselves. Sherman final drives, by comparison, could run for thousands of kilometers with minimal maintenance problems. The French confirmed this through actual operations from 1946 to 1950. The 150-kilometer failure showed up again and again. The Maybach engine, producing 690 horsepower, suffered continuous reliability nightmares. During the Battle of Kursk in July 1943, Operation Citadel, one Panzer unit experienced 20 fuel pump failures in just the first week. When these pumps failed, diesel sprayed onto hot engine parts. 3 Panthers caught fire and burned completely. 2 additional Panthers ignited while still sitting on the trains, bringing them to battle, never even reaching the fighting. Documented Maybach failures included cracked cylinder heads, broken connecting rods, destroyed oil pump shafts, engine fires caused by oil spraying onto blazing manifolds, failed cooling fan bearings, and constant overheating problems. German crews were ordered to reduce engine speed in November 1943. Instead of 3,000 revolutions per minute, the engine ran at 2,500. This extended how long engines survived, but it reduced maximum speed from 34 miles per hour down to 28. Power dropped from 700 horsepower to 580. Even with these limits in place, the average Maybach engine lasted only about 1,000 kilometers according to the French report. Some reached 1,400 to 1,800 kilometers at most. The Panther's turret system added complexity. Early models used a single-speed hydraulic system. A full rotation took 60 seconds. Later versions added variable gears. In high speed at optimal engine speed, the turret spun in 17 to 18 seconds. Shift to low gear or reduce engine speed, and rotation took 60 to 93 seconds. Performance changed constantly based on engine RPM. When the engine stalled, the turret stopped moving completely. No rotation. Nothing. The Sherman used an electric motor independent from the main engine. A Sherman's turret always rotated smoothly in 15 seconds. always. The tank commander could even rotate the turret when the main engine sat idle, using power from an auxiliary generator. This consistency provided enormous tactical advantage. The Panther's faster traverse sounded impressive on paper, but when mechanical failures killed the engine, it became meaningless. When tactical situations required the turret to move while the main engine idled, the Panther couldn't respond. The 7-speed manual transmission demanded brutal effort to operate. Every gear change felt like fighting a stubborn opponent. Sherman transmissions shifted smoothly, nearly automatic, effortless by comparison. The Panther's narrow tracks, despite calculations showing good ground pressure, meant limited actual contact with soft terrain. When Panthers ventured into mud or snow, they bogged down repeatedly. Their excellent performance existed only on firm, dry ground. Sherman tracks were wider. They gripped soft terrain, mud and snow much better. Real-world conditions favored the American design. The Panther's interior was cramped, dark and uncomfortable. The gunner had less working space than in a Sherman. The loader twisted into awkward positions, reaching across the massive gun breech to grab ammunition scattered throughout the fighting compartment. Everything felt wrong. Sherman ammunition storage featured ready racks positioned for convenient access. Everything was organized rationally. American automotive engineers designed the Sherman using principles from the automobile industry. Make it simple. Make it easy. Let the operator work efficiently. By March 1945, complaints from American tankers were flooding up to General Eisenhower. Tank commanders reported facing Panthers and Tigers. They wanted better machines. Eisenhower wrote directly to commanding officers, asking for detailed evaluations of American tank performance. General White, commanding 2nd Armored Division, prefaced his response by reminding Eisenhower that American soldiers liked to voice criticism, but their observations should be considered seriously. General Collier, commanding an armored regiment in 2nd Armored Division, provided detailed analysis. The opinion across the entire regiment was consistent. German tanks and anti-tank weapons possessed clear superiority in these areas. Better flotation, superior mobility, more effective gun sights, higher velocity projectiles, smokeless powder making German tanks harder to spot, superior armor sloping and better silhouettes. Collier then directly countered Eisenhower's suggestion that long shipping distances justified American equipment limitations. That doesn't make sense to our tankers, Collier wrote. Long-distance shipping shouldn't mean we accept inferiority. We deserve better equipment. This was March 1945. The European war would finish in May. Eisenhower's response came immediately. He sent Collier's report directly to General Marshall at the War Department. It was too late to change anything before the war ended. Yet these official assessments showed something clear. American tankers recognized the Panther's advantages in direct combat. They wanted better machines. They weren't blind to Sherman limitations, yet they won anyway. Not in spite of the Sherman, because of what the Sherman represented, a complete fighting system optimized for winning wars. Between June and December 1944, the 12th Army Group lost more than 2,000 medium tanks, most of them Shermans. When soldiers returned home and journalists reported the numbers, Americans were shocked. Tank casualties seemed impossibly high. In January 1945, a New York Times correspondent named Hanson Baldwin published critical editorials. He demanded Congress investigate American tank capabilities. Army leaders responded defensively, writing articles praising Sherman performance. General Levin H. Campbell, Jr., Chief of Ordnance, released Eisenhower's correspondence to settle the debate. After the war, General Marshall addressed the question directly. From the summer of 1943 through spring 1945, he acknowledged German Tigers and Panthers dominated Shermans in one-on-one fights. But Marshall's point was different. American doctrine never intended medium tanks to fight heavy tanks alone. Tank destroyers, artillery, and air support were supposed to handle heavy armor. Medium tanks had a different job. Exploit breakthroughs, support infantry. Different role, different design. The Sherman's record shows this when you look beyond individual battles. American and British forces invaded Normandy in June 1944. 11 months later, in May 1945, Allied armies stood in Berlin. They had advanced from the French beaches through France, Belgium, and into Germany itself. The war in Europe was finished. German forces with technically superior tanks couldn't stop this advance. Not because Panthers and Tigers were useless, they killed plenty of Shermans when they fought, but because they couldn't sustain operations long enough to matter strategically. A tank broken down before reaching battle contributes nothing. A tank immobilized by empty fuel tanks provides zero value. A tank waiting for spare parts that never arrive becomes a useless bunker. Strategic victory demands sustained operations across time and distance. The Sherman delivered sustained operations. The Panther didn't. The Sherman succeeded because it made the right choices. Not maximum gun penetration from extreme ranges, not thickest frontal armor against direct hits, but reliability, maintainability, crew survivability, production capacity, supply chain sustainability, tactical flexibility. The Sherman's 5-man crew configuration demonstrated this philosophy. Commander, gunner, loader, driver, assistant driver running the bow machine gun. Each position allowed efficient work and good crew coordination. Multiple escape routes meant surviving hits. A large belly hatch, side hatches, turret hatches. When a Sherman took a hit, crews escaped. The British studied captured Tiger tanks and used what they learned to create the Sherman Firefly with a 17-pounder gun. Different Sherman variants handled different needs. The M4A3E2 Jumbo carried 102mm armor on the glasses and 152mm protecting the turret front. Fisher Tank Arsenal rolled out 254 Jumbo variants between May and July of 1944. These powerful machines were earmarked as breakthrough tanks, meant to spearhead major assaults and punch through enemy defenses. The innovation that truly changed the game was the wet ammunition storage system, a feature that had been incorporated into Sherman production. This system housed ammunition inside water glycol-jacketed bins, a seemingly simple modification with extraordinary consequences. When a tank took a direct hit, the difference was stark and measurable. The older dry storage system saw ammunition ignite 70 to 80% of the time after penetration. The new wet system reduced that catastrophic probability down to just 10 to 15%. That single advancement meant thousands of crew members went home alive instead of becoming statistics in casualty reports. The lives saved by this one design choice were incalculable. The 76mm M1 gun made its debut in January of 1944, finally seeing actual combat that July during Operation Cobra. It offered noticeably improved armor penetration compared to the older 75mm gun. Yet this new weapon came with a serious trade-off that many crews would come to resent. The high explosive performance of the 76mm round was substantially worse than what the 75mm had delivered. According to official U.S. Army Technical Manual 9/1907, the 75mm M48HE round produced 950 effective fragments when it detonated, spreading lethal force across a 20-foot radius. The 76mm M1, by comparison, generated only 560 fragments. That reduction in explosive effectiveness represented a genuine tactical problem, and many units preferred to stick with what they knew worked better against enemy infantry. The tankers themselves understood their war far better than anyone in an office could. They knew the truth that tank battles against other tanks were actually the exception, not the rule. Their real fight happened against infantrymen dug into positions, against fortified locations, against soft targets that multiplied across the landscape. High explosive performance mattered more in the vast majority of actual combat situations than the ability to penetrate armor plate. The Panther's 270 gun, optimized relentlessly for anti-armor performance with its impressive velocity and long barrel, sacrificed explosive effect to gain that penetration capability. High-velocity weapons with long barrels simply could not simultaneously optimize for both armor piercing and blast effectiveness. Physics and engineering forced a choice, and the Germans had made their choice. The Israelis, however, saw something in the Sherman that others missed. They recognized its fundamental soundness as a design. They modified captured vehicles extensively, purchased additional Shermans when they could, and adapted them for their own needs. The M50 variant mounted a French 75mm gun and a Continental R975 engine. This version served continuously from the Suez Crisis in 1956, through the brutal Six-Day War in 1967, all the way to the Yom Kippur War in 1973. The Continental Mark I variant remained in service until its retirement in 1972. The Cummins-powered Mark II variant kept operating into the late 1970s. Then came the M51, which mounted a French 105mm gun. Beginning service in 1965, these tanks fought on into the early 1980s. Israeli M51s engaged modern Soviet T-54, T-55, and T-62 tanks using 105mm heat rounds, proving that the Sherman platform could handle contemporary armor threats through superior ammunition and gunnery rather than raw armor protection. Israel eventually sold 75 M51s to Lebanese militias in 1976 and sent over 100 more to Chile, which operated them continuously until 1999 and kept some in reserve inventory even into 2006. This remarkable operational span, stretching from World War II through the 1970s and 1980s, demonstrated the Sherman's enduring soundness, adaptability, and fundamental design integrity. The Panther presented a starkly different story of systemic failure. Production totaled approximately 6,000 vehicles between January 1943 and March 1945, not 9,000 as popular accounts often claim. Multiple authoritative sources have confirmed 6,000 as the correct figure, with some sources citing the precise number of 5,964 units built. Peak monthly production briefly reached 380 tanks in July 1944, but monthly averages ran far lower throughout its production run. At its operational peak on September 1, 1944, frontline combat strength reached 2,304 tanks. Yet that same September, a devastating record, 692 tanks reported lost in a single month. By the war's final operational report, dated March 15, 1945, only 361 Panthers remained operational out of 740 tanks on inventory. That meant barely half the Panthers still existed in fighting condition as the war wound down to its conclusion. Allied bombing played a significant role in the Panthers' decline. Daimler-Benz facilities took hits on August 6 and again on August 23, 1944. MAN's production facilities were bombed on September 3, October 3, and October 19, 1944, then struck again on January 3 and February 20 through 21, 1945. These bombing campaigns devastated the supply chain. Spare parts production collapsed dramatically, plummeting from 25 to 30% of tank production in 1943 down to just 8% by late 1944. Panthers in the field had to be stripped for components just to keep other Panthers running. The mechanical reliability problems that had plagued Panthers from the beginning were now compounded by this desperate shortage of replacement parts. Meanwhile, German crew training quality deteriorated sharply as the war ground on. Historian Steven Zaloga documented that the Panthers' disappointing showing during the Ardennes offensive against American Shermans, despite its technical superiority on paper, resulted directly from the poor quality of its crews by that late stage of the conflict. Most Panther crews lacked experience and received minimal training before being thrust into combat. Their inexperience magnified the Panthers' technical weaknesses rather than overcoming them. The combination of poor powertrain reliability, severe fuel shortages, inadequate spare parts, and inexperienced crews produced a cascade of failures. Panthers broke down in combat, and crews simply could not recover or repair them. A French military report from 1947 identified poor driver training as a principal cause of Panther mechanical failures. The assessment noted that battalions received drivers operating a Panther for the first time. Minor technical problems became death sentences as vehicles were written off and abandoned rather than repaired. German fuel shortages crippled entire armored operations throughout the final year of war. Panthers consumed enormous quantities of fuel, and German logistics infrastructure simply could not maintain adequate supply to forward units. Soviet hero Dmitry Losa commanded American-supplied Shermans on the Eastern Front and documented his experiences extensively. In interviews, Losa praised Sherman reliability with genuine enthusiasm. He noted that Sherman tracks routinely exceeded 5,000 kilometers of service life. The auxiliary gasoline engine for charging batteries particularly impressed him, eliminating the need to run the massive 500-horsepower main engine just to maintain electrical systems. Losa commended the superior American armor quality that produced no interior spalling that killed crews from ricocheting fragments. Crew stations were comfortable by military standards, and the overall mechanical reliability stood in stark contrast to Soviet designs. He observed that the Sherman drove like a car on hard surfaces, whereas the T-34 made so much noise that only the devil himself could know how far away it could be heard approaching. Cost efficiency enabled American mass production in ways the Germans could never match. Initial M3 and early M4 Chrysler contract prices in 1940 to 1942 ranged from $33,000 to $33,500. Later variants ranged from $44,556 to $64,455, depending on the specific model. By August 1945, official U.S. Army catalog prices listed most Sherman models at $44,000 to $55,000. Total Sherman production reached 49,324 documented units from 1942 to 1945, not the commonly rounded figure of 50,000. American manufacturers produced these vehicles across multiple factories using standardized parts and efficient assembly line methods. The Panther's base cost ran 117,100 Reichsmarks before weapons and radio. When equipped with the gun and full combat systems, the cost climbed to approximately 143,912 Reichsmarks per vehicle. German industry strained mightily to produce even 6,000 Panthers, despite investing enormous resources and effort. American tank doctrine emphasized integration of multiple elements. Shermans operated alongside infantry, with artillery support, tank destroyers, and air cover coordinating their movements. American commanders understood that pure tank versus tank engagements were relatively rare events. Most tank combat involved supporting foot soldiers, destroying fortifications, and engaging unarmored or lightly armored targets. The Sherman's reliable mobility and excellent high-explosive performance made it ideal for these actual battlefield situations. American tank destroyer battalions, equipped with M10, M18, and M36 tank destroyers, provided dedicated anti-armor capability when needed. The M36, mounting a powerful 90mm gun, could penetrate Panther armor more effectively than the Sherman could. During the Battle of the Bulge, M36-equipped battalions, including the 610th, 700th, and 740th, proved remarkably effective against German armor. 4 M18s, operating alongside M4 Shermans and infantry from the 10th Armored Division, held Noville north of Bastogne against a German armored attack. They used flanking fire to devastating effect, destroying 30 heavy tanks, including Panthers and Tigers. The Battle of the Bulge tested American armor doctrine under the harshest possible conditions. Hitler's Ardennes offensive, launched on December 16, 1944, with approximately 1,500 tanks and assault guns deployed across 24 divisions, including 10 panzer divisions committed to the main thrust. The initial German attacks crashed down on the 99th and 2nd Infantry Divisions. German forces achieved complete tactical surprise and enjoyed initial success. American units, including the 740th Tank Battalion, scrambled to respond to the emergency. Maintenance crews dug through depot stocks to assemble serviceable tanks, sometimes discovering dead crews still inside vehicles that reeked with the smell of death. They managed to put together 3 M4 Shermans and 1 M36 tank destroyer. On December 19th, this improvised force encountered elements of SS Lieutenant Colonel Joachim Piper's battle group, equipped with Panthers and King Tigers at Stoumont. The hastily assembled American tank force destroyed 3 Panthers, helping to blunt Piper's spearhead. Throughout the Bulge campaign, American tank destroyers proved their battlefield value repeatedly. Towed anti-tank guns proved entirely ineffective in the cold, wet weather across rough, broken terrain. Across First Army, three-quarters of towed tank destroyers that were lost became total losses, destroyed or abandoned beyond recovery. The 801st Tank Destroyer Battalion, equipped with towed guns, lost 17 guns in just 2 days. The 614th Tank Destroyer Battalion, equipped with M10 self-propelled guns operating nearby, found ideal opportunities for close-range ambushes. This unit claimed 17 German tanks destroyed during the same period. The contrast convinced Eisenhower to authorize conversion of all remaining towed units to self-propelled guns by January 1945. The M36, just beginning to reach frontline units when the offensive commenced, proved highly effective throughout the Ardennes campaign. Its 90mm gun, the same armament found on the M26 Pershing heavy tank, arriving at the front, could engage Panthers and Tigers on more nearly equal terms. American logistics made sustained operations possible. Sherman engines ran on readily available gasoline. Spare parts flowed continuously from American factories to frontline units. Maintenance could be performed by adequately trained crews without requiring specialized expertise. Battle-damaged Shermans were recovered from the field, repaired in mobile shops, and returned to combat operations rapidly. The U.S. 3rd Armored Division entered combat in Normandy with 2,132 M4 Sherman tanks. Across the entire European campaign, the division lost approximately 648 Shermans, completely destroyed in combat. Another 700 were knocked out, but recovered, repaired, and returned to active duty. That 580% loss replacement rate sounds catastrophic on the surface, yet it demonstrated the Sherman's greatest strength: the capability to be produced in such vast numbers that losses could be continuously replaced, the capability to be recovered and repaired when damaged, the logistic system that kept replacement tanks flowing forward to sustain operations. German armored divisions, by contrast, watched their strength decline steadily throughout the campaign as losses accumulated faster than replacements could arrive. The Battle of Aracourt in September 1944 demonstrated American tactical superiority despite overall technical inferiority. The 4th Armored Division's 37th Tank Battalion, commanded by Lieutenant Colonel Creighton Abrams from his Sherman Thunderbolt, engaged German forces including newly arrived Panther-equipped units. Abrams went through 7 different tanks during his war service, but always commanded Shermans. At Aracourt, his battalion lost 14 Shermans while destroying 55 Panthers and Tigers. General Patton called Abrams the world champion tank commander. This single engagement proved that properly deployed Sherman tactics, utilizing terrain, coordinating arms effectively, and aggressive maneuver could defeat technically superior German armor. The Sherman alone did not win World War II, but American armored divisions equipped with Shermans spearheaded the breakout from Normandy, the drive across France, the crossing of the Rhine, and the conquest of Germany itself. They accomplished this while facing German forces equipped with Panthers, Tigers, King Tigers, and Jagd Panthers. Technically superior German armor could not stop American armored operations, because wars are not decided by technical specifications alone. Logistics wins wars. Reliability wins wars. Production capacity wins wars. Combined arms integration wins wars. Crew confidence wins wars. Adaptable doctrine wins wars. The Sherman embodied all these winning factors. The Panther embodied impressive specifications but failed at systemic integration. When Soviet forces captured Panthers and attempted to use them against German forces, the vehicles performed briefly, then broke down. A February 1945 Lower Silesian offensive saw one captured Panther with an experienced crew from the 4th Tank Corps under command of hero of the Soviet Union, Lieutenant Nikolai Ivanovich Adhaev, dispatched on a reconnaissance mission. At dusk, the tank moved through forest, attacked German positions from the flank, and destroyed 3 enemy Panthers. During retreat back to Soviet positions, German artillery struck the tank and damaged it severely. After the engagement, the tank was written off. Lack of spare parts and mounting maintenance problems made continued operation impossible. Even when operated by skilled Soviet crews, captured Panthers proved unsustainable. Effective tank analysis must account for the entire weapon system: design quality, manufacturing capacity, supply chain logistics, maintenance infrastructure, operational doctrine, crew training, tactical employment, and long-term sustainability all matter equally. The Panther excelled at a narrow set of specifications: gun penetration at long range, frontal armor protection in direct firefights, and speed across good terrain. But it failed catastrophically at reliability, maintainability, production efficiency, supply chain sustainability, crew ergonomics, escape provisions, and operational availability. The Sherman provided adequate performance in gun and armor specifications while excelling at reliability, maintainability, production efficiency, supply chain sustainability, crew ergonomics, escape provisions, and operational availability. In total war, adequate technical specifications combined with superior systemic factors defeat superior technical specifications combined with inferior systemic factors every single time. This lesson transcends World War II. This lesson transcends tank design itself. Any weapon system, any tool, any technology must serve its users under real-world conditions. It must function reliably when needed most. It must be maintainable with available resources and existing infrastructure. It must account for human factors in operation and maintenance. It must integrate effectively with other systems. It must align with operational doctrine. It must remain sustainable through the supply chain. It must be producible in quantities that meet actual demand. Technical excellence that ignores these factors produces expensive failures that look impressive on paper but collapse under operational stress. Practical adequacy that embraces these factors produces war-winning tools that perform reliably under the worst conceivable conditions. The Panther's development, rushed into production after encountering T-34s, never achieved the maturity needed for reliable field operations. Its combat debut at Kursk in July 1943 proved disastrous with widespread mechanical failures. Subsequent improvements reduced but never eliminated the fundamental design flaws. The final drive problem, rooted in weight growth beyond original design parameters, was never solved. Engine reliability improved somewhat, but remained poor compared to Allied tanks. The design complexity exceeded German industrial capacity to manufacture with adequate quality control, especially as Allied bombing damaged factories and disrupted supply chains. The Panther represented German engineering's tendency toward over-optimization for specific parameters at the expense of overall system effectiveness. The Sherman represented American industrial pragmatism: design for manufacture, design for maintenance, design for logistics, design for the crew. The Sherman was never intended to be the best tank by any single metric. It was intended to be good enough at everything, while being excellent at factors that mattered most for sustained operations: reliability, maintainability, producibility. American automotive industry mass production expertise, applied to tank manufacturing, created a weapon system that could be built by the thousands and sustained across global supply lines. Ford, Chrysler, General Motors, American Locomotive Company, Baldwin Locomotive Works, Lima Locomotive Works, and Pacific Car and Foundry Company produced Shermans using standardized components and efficient assembly methods. The last Panther rolled off production lines in March or April 1945. By then, many were being abandoned before even reaching combat units due to lack of fuel and trained crews. The last Shermans rolled into Berlin in May 1945 as the war in Europe ended. Israeli-modified Shermans fought in the Yom Kippur War in October 1973, nearly 30 years after the war concluded. This operational longevity gap of 3 decades between the Panther's extinction and the Sherman's continued evolution illustrates which design philosophy ultimately proved more sustainable and effective. The Panther turned out to be a technological cul-de-sac. Nothing that came after the war drew any substantial lessons from its design. The Sherman, by contrast, left an imprint on tank development everywhere it went. The reason was fundamental. The Sherman's creators had struck the right balance, fusing reliability with maintainability into a package that could actually fight. That balance proved to be exactly what real warfare demanded. American tank crews in 1945 didn't need military theory to understand this. They had lived it. They'd encountered Panthers face-to-face in combat. They'd walked across battlefields and seen abandoned Panthers sitting silent in the dust. Some of their units captured Panthers and studied them closely. Those crews could see what Panthers did exceptionally well in head-to-head tank fights. But they also saw something else, something that mattered far more. They saw the Panthers fall apart when asked to do the one thing tanks must do: keep operating. A tank that breaks down before it reaches the battlefield isn't a tank anymore. It's scrap metal. A tank that gulps fuel faster than supply trucks can deliver it becomes immobilized by its own hunger. A tank that needs replacement parts that don't exist anywhere in the field sits abandoned because there's no way to fix it. When a tank gets hit and the crew can't escape, it becomes a coffin. The Sherman earned its grim nickname, Ronson Lighter, because ammunition storage in the early models had a real problem with catching fire. Men died because of this. American engineers didn't ignore it. They developed wet ammunition storage and cut the fire danger dramatically. German engineers did nothing similar for their Panthers. They never tackled the survivability problem. Yes, the Sherman's armor was thin, genuinely vulnerable in direct tank-on-tank encounters. American commanders responded by changing how they fought. They stopped throwing tanks at each other head-on whenever possible. Tank destroyers handled anti-tank work. Infantry, artillery, and air support worked together with the tanks to achieve results. The Germans went the other direction. They kept building heavier and heavier tanks, vehicles so massive their engines couldn't handle them, so expensive that building enough of them became impossible. One approach succeeded. The other one didn't. The numbers tell the story plainly. Almost 50,000 Shermans rolled off production lines, 6,000 Panthers. By March 1945, Sherman tanks were available and working more than 80% of the time. Panthers were broken down more than half the time. American armored divisions stayed combat effective all the way from Normandy to Berlin. They suffered terrible losses, but the system kept replacing those losses. German armored divisions got weaker and weaker as the campaign dragged on. Their losses piled up faster than they could replace them. American combined arms doctrine worked because it integrated everything: tanks, infantry, artillery, air support, specialized equipment. German doctrine tried to make tanks carry the entire load as infantry and artillery capabilities shriveled away. Understanding why Sherman won means looking at American industry before and during the war. When America entered the fighting, the great automobile manufacturers simply converted their factories. Ford's River Rouge plant transformed. Chrysler's tank arsenal came into being. General Motors factories shifted gears. They didn't build military vehicles from scratch. They adapted the assembly line methods they'd perfected making cars. Workers who'd spent years on automobile production lines brought that same efficiency to tank building. Parts became interchangeable across different factories. A transmission built in one location fit a hull made somewhere else. Gun mounts from one arsenal matched turrets from another. This standardization, routine in the automobile industry but revolutionary in military manufacturing, allowed production rates nobody had seen before. It made field repairs simpler too. Every Sherman design decision reflected one priority: can we make this in massive numbers without needing specialized equipment? Curved armor plates look better and stop more rounds, but they demand expensive dies and specialized presses. The Sherman used mostly flat armor that could be cut and welded by ordinary workshops. The turret was cast in large foundries using techniques borrowed from civilian heavy industry. The suspension relied on vertical volute springs, simple and dependable, manufactured by companies that had zero military background before the war started. Nothing in the design required tools or techniques that didn't already exist somewhere in American industry. Training crews took about 3 months at the training centers. Most of the work felt familiar to men who understood cars and trucks. Everything worked the way soldiers expected it to work. The manuals were clear enough that mechanics with just basic automotive knowledge could follow them. Panthers required longer training. The complexity demanded it. As German losses mounted and training time got cut shorter, the crews got worse. American training kept its standards steady the entire war. The pipeline produced qualified crews whenever combat demanded them. The Sherman's maintenance advantages showed themselves over long campaigns. Swapping out an engine took a trained crew 8 to 10 hours if they had proper equipment. The engine and transmission came out as one unit, a power pack that trucks carried along with advancing columns. A Sherman disabled in the morning could be fighting again by afternoon. Panthers were different. The engine and transmission were separate pieces, each requiring its own removal process. Field repairs became nearly impossible. Tanks got towed miles back to proper repair facilities. Plenty of Panthers were simply abandoned after small mechanical failures because fixing them in the field wasn't realistic. A Sherman's tracks could be replaced by the crew working right there beside the vehicle. 3 to 4 hours per side. 2 men could handle the track blocks without much strain. Panther tracks were heavier and stubbornly difficult. The interleaved road wheels looked good in specifications. They gave a smooth ride, but if one inner wheel got damaged, you had to remove multiple outer wheels first to reach it. Winter made it worse. In cold, mud froze between those interleaved wheels and locked the whole machine solid until you spent hours thawing things out. Shermans with simple, straightforward suspensions didn't face that particular nightmare. Shermans needed an enormous logistics tail. There's no getting around that. Each armored division consumed thousands of tons of fuel, ammunition, parts, and supplies every month. American logistics kept delivering anyway, across distances that grew longer as armies pushed through Europe. The Red Ball Express, a truck convoy system designed purely to haul supplies, moved 7,000 tons daily at its height. Liberty ships brought material from American factories across the Atlantic. The system functioned because it was conceived as one unified operation, then resourced and executed as such. German logistics did something different. It collapsed. Allied bombing destroyed railways, fuel refineries, and transportation networks. Panthers might run mechanically sound, but fuel doesn't appear out of nowhere. They burned fuel at tremendous rates. Sherman fuel consumption was equally heavy, yet American logistics kept the supplies flowing. The issue wasn't how much fuel each tank wanted. The issue was whether the supply system could deliver it. American logistics was engineered for mechanized warfare on a planetary scale across ocean supply lines. German logistics was designed for quick campaigns contained in Europe. It shattered under the weight of sustained fighting and constant Allied attacks on the supply lines. Sherman succeeded because it represented a complete military system. Sherman design, production methods, training pipeline, maintenance procedures, logistics support, tactical doctrine, all of it worked together. Panther failed because it was engineered as a technically outstanding weapon without building the system to support it in actual combat. Wars aren't won by weapons. Wars are won by systems. Whichever side builds the better system defeats the other side, even if that other side has superior weapons. The United States during the Second World War constructed and maintained a military system capable of projecting force across the entire globe, supplying armies across oceans, keeping equipment functional in terrible conditions, training replacement personnel continuously, and adapting tactics as situations changed. Germany built increasingly complex weapons that its factories couldn't produce in sufficient numbers. Its supply network couldn't sustain them. Its training system couldn't provide adequate crews. Its tactics couldn't deploy them effectively when resources ran low. Professional soldiers studied this afterwards and reached the same conclusions. French forces operated captured Panthers from 1946 until 1950 with the 501st and 503rd Armored Regiments. They documented every breakdown, every operational difficulty, every limitation. Their 1947 technical report became the standard work on what Panthers actually did when pushed through real military service. The assessment confirmed the harsh realities. Engines lasted about 1,000 kilometers, final drives about 150. Maintenance proved complicated, fuel consumption was brutal, crews were miserable, tactical flexibility didn't exist. French engineers and tankers had started out impressed by what the Panthers looked like on paper. After running them in actual operations, they concluded the Sherman was genuinely the superior fighting machine when you factored in everything that mattered. Certain Panther features were genuinely excellent, particularly the gun and optical systems, but the entire package simply wasn't built for sustained military operations. The British reached identical conclusions. They captured numerous Panthers during their campaign in northwestern Europe. After Germany surrendered, British commanders took over a Panther assembly facility at Hanover and had German technicians complete 9 additional Panthers using components still sitting around. These 9 British-made Panthers, finished in spring 1946, were supposed to get thoroughly tested. Standard armoured vehicle trials went forward on 2 Panthers and 2 Jagdpanthers. The testing stopped when the last functional Panther damaged its transmission climbing a hill. All the other Panthers had either been stripped apart for spare parts or had simply stopped working from mechanical failures. The report, filed in February 1948, stated that almost nothing of any value came from the testing. The fundamental reason was the Panther's consistent mechanical unreliability. France and Britain independently discovered that captured Panthers made interesting technical studies but were operationally useless. American testing happened at Aberdeen Proving Ground in Maryland with captured Panthers, though the detailed reports haven't circulated as widely as the French assessment. The facility tested captured enemy equipment from every war front. American engineers saw the Panther's advanced features and also documented its many flaws. The knowledge shaped post-war American tank development, but not by copying Panthers. American engineers learned what not to do. They learned how chasing specific performance numbers creates systems that break down under real-world demands. They learned how adding complexity without matching reliability produces weapons that don't work. They learned that impressive performance specifications mean nothing when the vehicle can't operate in actual combat. The Panther became a dead end. The Sherman went the opposite direction. Many Second World War weapons remained in service decades later or shaped post-war development significantly. Spain and Czechoslovakia kept building German Me-109 fighters into the 1960s. Mauser rifles served armies worldwide after the war. Panthers vanished. No nation kept operating them after captured stocks ran out and spare parts disappeared. The Soviets captured hundreds of Panthers, used them briefly, then threw them away. Czechoslovakia and other Eastern European countries operated captured Panthers for a while before quickly replacing them with Soviet designs. France and Britain tested them thoroughly, made decisions, and moved on. No subsequent tank design anywhere incorporated meaningful lessons from Panthers. The design simply didn't influence post-war tank development in any significant way. Sherman went forward continuously. The basic M4 adapted to dozens of specialized roles: tank recovery vehicles, armored personnel carriers, self-propelled artillery, rocket platforms, bridge layers, mine clearers, and flamethrower vehicles all used Sherman chassis. The design could stretch to do things far beyond its original purpose. Israeli engineers modified Shermans that fought effectively in the 1960s and 70s against Soviet-designed armor. The M50 and M51 represented complete rebuilds, keeping only the basic hull while upgrading essentially everything else. Israeli Shermans carried French guns, American or British engines, improved suspensions, modern fire control, better armor. The fact that these vehicles succeeded demonstrated the Sherman design remained fundamentally sound enough to accept improvement for decades. Panther design allowed no such flexibility. Its complexity and tight integration made modifications impractical. The vehicle was optimized for its original configuration and couldn't adapt to anything else. Sherman represents one of history's most successful weapons, not because it was perfect, not because it excelled by every single measure, but because it was adequate technically, reliable, maintainable, producible in enormous numbers, and trusted by the crews fighting in it. That mixture of sufficient technical performance with superior systemic factors created a weapon that won. Panther shows what happens when technical excellence operates separately from systemic requirements. Impressive specifications matter very little when the weapon can't arrive at the battlefield, can't stay operational under combat conditions, can't be built in necessary quantities, and can't be effectively operated by the crews available. Technical excellence without systemic integration creates expensive, unreliable, unsustainable failures, regardless of how impressive the design looks in technical documents. History rendered its judgment. Sherman won. Panther lost. Not in any particular battle, but in the broader campaigns. The production competition, the logistics competition, the sustainability competition, the reliability competition. American tankers grasped this completely. They experienced it firsthand. They fought in it. They won because they understood it. 79 years later, the lesson remains unchanged. Wars get decided by systems, not by weapons. The side that builds the better system, even with adequate rather than superior weapons, defeats the side with superior weapons but inadequate systems. The debate between Sherman and Panther concluded in May 1945 when American Shermans drove through Berlin while abandoned Panthers littered the highways where the German army retreated. The debate shouldn't have existed at all. To anyone who grasped that genuine military effectiveness gets measured by actual results instead of specifications, the answer was always plain.